Hello, AP Calculus folks. My name's Mr. McAllen, but what we're going to do today is we're going to talk about what a linearization is, what it's used for, how it's kind of like cheating in mathematics, and then we're going to find a linearization of a given function, and then use the linearization to approximate a function at a point. So let me explain to you what a linearization is. Imagine yourself living in a world without calculators, but you have to figure out what a value of a function is. For instance, let's say you need to know what the square root of 23 was, but you didn't have a calculator and you didn't want to be doing guess and check your whole life. So what you would do is you would use a linearization to help you figure this out. Let me show you through examples how this works. First thing is we need to come up with what the linearization equation is. So I have a little do now for us. And what we're going to do is we're going to just do kind of what we know already, because we should know already how to find an equation of a tangent line. Remember, the goal of what we're doing is it's kind of like mathematical cheating, but it's not really cheating. We're just doing an approximation to make finding the value of a function easier, or, well, we're going to get close, but we're not going to really get the value, but we're going to get pretty close. And I'll show you what I mean in a minute. So first we have this function. It's the square root of 1 plus x. So I'm hoping that you guys know from your transformation of functions that the square root of 1 plus x is a square root function moved to the left by 1, and we're going to do a linearization at 0. So that means that when we draw our tangent line, it should look like that. Now, if you notice, the tangent line is really, really close to what the square root function is. In a certain space, they're actually the same. Well, they look the same on a graph, which to us, we could kind of call them the same. They're not really the same, except for at the point of tangency where they actually touch once. But your eyes kind of tell you that they're almost the same, like between these x values. So as a result, we can kind of use that as a good approximation. It'd be much easier to figure out the value of those functions around those points as opposed to finding, like, for example, let's say I want you to find what the square root of 0.5 was. You wouldn't want to have to do that by hand, but using this linearization at 0, you could. Well, let's first do what we know. Let's find an equation with tangent line. Let's find, remember how we did y minus y1 equals m times x minus x1? We're going to come up with that equation of tangency, and we're going to go through the parts of calculus that help us get that. So remember where, for example, uh, if we're doing it y equals 0, all right, do you know what the y value would be when x equals 0? Okay, so here, let's write out the equation. Y minus y1 equals m times x minus x1. And I'm going to replace the x1 with, you probably guessed it by now, 0. I'm going to replace the y1 value with what this function is when I plug x equals 0 into that. So you guessed it, y minus 1. Where do I get the m value from? Well, the m value, the slope of the curve at that point of tangency, is the derivative. So we need to figure out what f prime of x is. And if you guys remember, I told you, when y equals the square root of x, and I said, the derivative is just a nice easy shortcut, just 1 over 2 root x. And that's what, f prime of x is. It's 1 over 2 root 1 plus x. This is kind of a review for a lot of you people. This isn't like the first time you've seen this. So f prime at x equals 0 will be 1 over 2 root 1 plus 0. As a result, you'll have 1/2 as your slope. So I'm going to just go down here, and I'm going to write y minus 1 equals 1/2 of x minus 0. This, believe it or not, is a linearization equation. If I solve it for y equals, I have 1 plus 1/2 of x, because that 0 part isn't there anymore. This is an equation of a line. That is this tangent line's equation. And instead of calling it y equals, we get a little fancy, and we call it L of x equals 1 plus 1/2 of x. Let's see how close this function really is to the curve. So I'm going to go to Desmos, so I just don't want you guys to miss me. So here's my computer screen. That's probably weird. Okay, so here, let me just go to, all right, so I'm going to go to Desmos, and I'm going to have, here's my function, 1 plus x. See how it moved over to the left by 1. And now I'm going to put my linearization in. L of x equals 1 plus 1/2 of x. So see that? See how it's tangent right there? Let me change the color of this. That's like really not so good to have that same color because you can't tell the difference. So I'm going to use a green line, or let's say a blue line. Okay. So now I'm gonna go back and I'm gonna make a table out of this. So you could see my L of x, and let me see if this will take f of x. I really need. Okay, so here's f of x. So watch, check this out. See how if I put in at 0, and let me go, we said we were going to look at what the value of 0.5 was, right? So here I'm going to put 0.5 in. Now, the linearization says it's 1.25, right? But the actual function value is 1.2247. So it's kind of close, but it's not. But it's a lot easier to calculate the approximation with the linearization than it is to actually do all the guessing and checking to find out what the square root of 0.5 is. I don't know if you really understand this or not, but we're going to do another example, so don't worry. So remember, the idea of a linearization is it's going to let us calculate a value to approximate a function that's really close to a point of tangency, but it's not going to give us the exact value because there's some error. We're trying to fit a curve. I'm pointing to the screen, but you can't see that. We're trying to fit a curve to a straight line. So the line is going to break away from the curve, and the amount that it breaks away is going to be our error in the approximation. I hope I'm making sense. So what I'm going to do now is I'm going to do another example. Let's do it with a trig function. Let's see what that would look like. So I'm going to go back to OneNote. This looks like a big old mess of information. I'm going to write out for you, so maybe you want to take a note here. L of x is equal to my function value at a. A is the x value for the center of the approximation. This is where you have your point of tangency. A is a value of x for where the curving function and the straight linear function, they touch, and they share the same x and y value. So, plus, now this is going to be the derivative at a times x minus a. Remember, a is the special point of tangency. Everything has to be figured out at a. We have to figure out our derivative at a, our y value at a, and we have to put it in the last part of x minus a. So here we have our second example. Pardon me. We want to find linearization of a cosine function. Now, can you imagine trying to find the cosine of 1.75 radians without a calculator? I would not want to do it. But with linearization, we get to do things a little bit easier. So we're going to consider our center point of our approximation to be pi over 2. Now, you may say, well, why pi over 2? Pi over 2 is 3.14 divided by 2, which is equal to 1.57 radians. That's not too far away from 1.75, so I'm going to say that might be okay. So I'm going to draw a picture of cosine just to illustrate what we're doing here. Cosine starts at 1, and by pi over 2, it's going through 0, and it's going to do this kind of thing. So, and this is kind of an exaggerated sine function, but here would be my tangent line. So I know you're not really thinking this is a great idea, but this is like an exaggeration. Well, I don't know how I really feel about this, but you get the idea. That at 1.75, let me try to clean this up a little bit. The picture's worth 1,000 words, and I don't want it to be. So here's my The blue line doesn't work either. Let me go with a red line to show the tangent line equation. So do you see how the tangent line and the cosine function kind of share the same space? So if pi over 2 is 1.57, and I'm going to go out to 1.75 radians to approximate it, do you see how they're kind of like almost the same value? I'm going to say that's good enough for me because I live back in maybe the 18th century and I don't have a calculator. So I'm going to try this out. So here we go. Let's write down our linearization equation. And I'm going to write L of x equals f at a. Now remember, a is the center point of the approximation, plus the derivative at a times x minus a. Now let's get all these pieces of the puzzle in place. Remember, this comes from what we've been doing for the last, I don't know how long, as we've been doing equations of tangency. Y minus y1 equals m times x minus x1. All this stuff comes from that. So here, remember f of x is the cosine function. A is pi over 2. So we can figure all this stuff out. So f prime at a is cosine, negative sine of a. So now we know, okay, so let's figure out f at, we have to figure out, let me write this out here. L of x is equal to f of a is really f at pi over 2 plus f prime at pi over 2 times x minus pi over 2. What did I do from this step here to this step here? I just replaced a with pi over 2. That's it. Because it's pi over 2 and I'm talking about the cosine function, I can figure out these values pretty easily. So I'm going to put in L of x equals f at pi over 2 is the cosine at pi over 2, which is 0. All right, that's cool. And then we have f prime at pi over 2 is the negative sine from over here at pi over 2, which is equal to negative 1. So I'm going to put negative 1 here. Now I have x minus pi over 2. Okay, let's see how this is going to work out. So my linearization function is equal to negative x plus pi over 2. I just simplified this line here. So now let's figure out what the linearization says for 1.75. The linearization at 1.75 is going to be negative 1.75 minus plus, because remember this minus and that minus make a plus, plus pi over 2. Now pi over 2 is 1.57. There might be more decimal places, so I'm not going to worry too much about that, because remember I don't really have a calculator either. Negative 1.75 plus 1.57. Now because I don't have a calculator, I got to do this the long way. I got the difference between these two is negative 10, negative 18, negative 1.75, and let's just see what the difference is. 1.57. This is carried. You got 8, and then here we got 6. So it's like 0.18. So the difference is going to be negative 0.18, and that's what I'm approximating. Okay, so let me explain what's going on. I'm saying that the cosine of 1.75 radians is going to equal approximately now it should be negative 0.18. You know why I knew it was negative was because it's below the x-axis. Okay, I'm just going to check to see how much time we have. I've been going at it for 14 minutes. So here, let's go to Desmos and verify this and make sure it's all working out. Okay, so all right, here we go. I'm going to go to Desmos, and on Desmos, I'm going to just clear out this function, and I'm going to clear out this table and this function. I'm going to put in cosine of x. You can see there's our cosine function. I'm going to put, let me put a point of pi over 2, comma, f of pi over 2 to show you, oh, I have to do this, f of x equals, there we go. All right, so now you can see the black point here. That's a point of tangency, right? Okay, can you see me? All right, so now here's my equation. I think it was L of x equals, I think it was negative of x minus pi over 2. All right, there it is. See that? See how it's like such a perfect line between the two? Let's look at a table of this function. And I'm going to just go to make a table. Let's see. I'm going to make a table of that. And then I'm going to put over here f of x. I really need to learn to type. Okay, so now look. The values of the table aren't so great. So here, I'm going to like just put in here a value of 1.75. And now you can see, here's my linearization, negative 1.179 negative. I said it was negative 1.8. That wasn't too bad. And look at this. This is the actual amount of the function. So in a day where you didn't have a calculator, what way would you rather do this calculation? I hope you say my way. With linearization. And this is what calculus was used for, to help you figure out approximate values of functions a long, long time ago, before you actually had a calculator to figure it out. Now, there are going to be other things that we're going to learn about this, especially if you travel down the road of BC calculus. We're going to learn how to use extra derivative terms to, I'm pointing to the graph, but to bend this like approximation to make it curve to follow the cosine function better. But for now, we're just working with a linearization. We're not talking about curving it in any way. I hope this video has helped you understand what a linearization is used for, and I hope you can understand how we want you to do the problems in the textbook to really do this type of work. So anyway, look forward to hearing your comments, and I'm sorry this video went a little long, but the concept is pretty deep, and I want you to understand exactly what it was used for in the day that it was created. And this also led to other things in mathematics, such as Taylor polynomials, which actually are used to fit much more curvy functions in this. Anyway, take care. Look forward to hearing your comments, and tune into the next video where we're going to talk a little bit more about differentials and what we use those for.